Alright, in this video we're going to discuss magnetic flux. And magnetic flux is very similar to the electric flux. We're attempting to establish how much of the field is going through a particular surface area. However, instead of counting electric field lines, essentially, we're counting magnetic field lines. So I've drawn the edge of a face of a box. So our magnetic field is going through, for this example, a square sheet. So our flux would be coming out of the page through this rectangular surface. So it's one face of a box. So that's what I've drawn here, edge on. Once again, we define the n hat vector, or the direction of that area, as perpendicular to the surface. So if our magnetic field line comes at an angle, we want the component of that field that is perpendicular to the face of the box or parallel to n hat. And since we want that our angle is between, perpendicular to the surface, and the electric field, we're defining this angle phi in here. That phi is adjacent to the n hat direction. So if I make a right triangle in here, this would be B perpendicular. I already have B parallel drawn in. We want to use cosine because that gives us the component of that triangle, or the component of the field that's in the same direction as perpendicular to the surface. So down here I've done that the magnetic flux is equal to the magnetic field strength times the area times the cosine of phi, because that gives us that parallel component. Now up here I have one with an integral. We would use this one whenever the field is not uniform over the entire area. So if the magnetic field strength is a function of area, then we need to integrate as well as doing the dot product in order to get that parallel component aspect in there as well. Our new unit for magnetic flux is going to be a Weber. So unlike electric flux, magnetic flux actually has its own unit. It's called the Weber, represented by WB. Is the same thing as a Tesla meter squared. Now what's a little bit different when we discussed electric flux compared to what we're talking about now with magnetic flux is when we talked about electric flux, we went on to talk about Gauss's law. We did the integral of E dot dA equals Q enclosed over the electric constant. And the problem we're going to run into is that if we put a magnet in the box, there is a north and a south pole. And we've already discussed earlier, there's always a north and south pole. Even if I split this magnet in half, we just have two magnets, both with a north and a south pole. This is different than with electric fields because we could have a Q enclosed that was a net Q enclosed. So we could have 3Q in there by itself, or you could have 3Q and 2Q and end up with a Q enclosed of a positive Q. Here, we're always going to have a north and a south pole no matter what we try to stick inside of our enclosed surface. So this is now a rectangular prism rather than one face of a box that we did over on the left-hand side. So we could before had an option to put a charge in and therefore have an electric flux come through the surface of the rectangular prism, or we could put a positive Q and a negative Q and have them cancel each other out and have no net flux through the surface area of the enclosed rectangular prism. Here we're always going to have a north and a south pole. So no matter how many magnets we try to shove into this box, there's always going to have one where you come out of the north and into the south, and that's going to always happen because we cannot find isolated magnetic poles in nature. So that means when we do the integral of B dot dA equals pole enclosed over the magnetic constant, we end up with 0 every single time because there's always going to be a positive pole and a negative pole, and they're always going to cancel each other out. So the integral of B dot dA is equal to 0 for an enclosed surface. Now over here we can get a flux because we're just going through one face. But here there's going to be flux coming out of the top of the box that then comes around and comes back into the box from the bottom. So there's always going to be a corresponding out and in that cancel each other out. So there is no magnetic flux when you have an enclosed surface.